Hi, everyone. Thank you for joining Open Source Data Summit, and thank you for interest in this session. I'm going to talk about building data analytics platforms with open source, why, and actually how to do that on Kubernetes. This talk is based on my experience in the rapidly changing data domain, discussions within specific groups and communities, and might be considered as opinionated. Who am I and why I'm here? I'm a data platform engineer. What does it actually mean? Well, first of all, it means that I'm a data engineer, so I know data engineering problems. Also, I'm a backend developer with a strong Java background, but also use Python. Next, I'm a DevOps practitioner who truly believes in DevOps culture and principles. And last but not least, I'm independent open source contributor. I contribute into different projects in my free time, so it's one of my hobbies. Today, I'm presenting here because last 2 years I worked in healthcare domain where inability to use public clouds like AWS, Google, and Azure is one of the main limitations to the utilization of all latest and greatest ready-to-use products that exist in rich data world. The talk will follow this agenda. First, introduction slides with some terms and definitions which I think are important in the talk context. Then I will introduce an overall architecture and key principles for an open data platform. Then we will build reference architecture step by step. In this part of the talk, I will give an overview and share some specifics of the open source products, and it will be quite intense, so bear with me. And finally, we will discuss whole platform management. Okay, let's get started. What is a data platform? You can find different definitions, but in short, it is the solution designed to collect, store, process, access, and manage data. Also, from another angle, we can say that it is a set of integrated tools, processes, and practices that allow to solve data-related problems and enable business for effective utilization of data for operation and decision making. Then, what is Open Data Platform? Open Data Platform is a data platform based on open technologies, open standards, and community principles, which is very important. So, why Kubernetes? Why not use services provided by cloud-based platforms? Well, if there are no issues to consider within your business or business domain, public cloud is a great choice. Go ahead with it. It provides easy access to a plethora of highly integrated services inside and outside the platform, and it's great. But there are some cases where you cannot use cloud-based platforms. For instance, public sector might limit you by requirement to run workloads on-prem, or healthcare regulatory that has a strict rule to store and process the data within a certain region or within a specifically certified data center. In such cases, Kubernetes is a great choice. It simplifies workloads, operation, and scalability, and today it's standard de facto for container platforms. Kubernetes allows to build cloud-native and cloud-agnostic solutions at the same time. No vendor lock and ability to use hybrid clouds. Next thing I would like to cover is application package management. Application might consist of several components. For instance, backend, frontend, cache, nightly scheduled maintenance job, and so on. It means that many coupled Kubernetes resources need to be managed together, created, updated, deleted. There are a few options to package Kubernetes resources together, but Helm is the most popular and widely used option. Helm has concept of repository where you can find packages called charts with resource templates. Then all you need to deploy an application to your Kubernetes cluster is the following. Make sure the repository was added to your repository list. Run helm install command with provided chart name, and properties you want to write to. So existing Helm chart for an application made this application accessible for Kubernetes users, and it's one of the key requirements for building platforms on Kubernetes. Last but definitely not least, GitOps. GitOps is an operational framework for managing infrastructure and applications using version control system as a single source of truth. In GitOps, the desired state of a solution is defined declaratively and stored in version control system. Usually it's Git, so that's why it's called GitOps. All changes to the system are made via commit to Git repository. Then automation tool or agent periodically compares desired state from repository and actual state in destination environment. And in case they are different, the agent tries to propagate changes to achieve the desired state. What can be managed this way? Well, quite a lot of things. For instance, it might be Kubernetes cluster with number of nodes, their sizes, and so on. It might be applications. You can control number of replicas or application configs. It might be data pipelines, dashboards, and so on. Great. Now I'm done with the long intro. Let's start with designing the data platform. So what are the key principles and criteria for building open data platform on Kubernetes? First of all, it needs to be open source based. Only open technologies and open standards should be used. Yes, it's fine to use proprietary implementations or SaaS, but they should be based on open standards. Active community is one, or as I said before, the community that is open for new members, open to review new changes, new proposals, and appreciates any form of contribution. Secondly, it should be Kubernetes native. Ideally, components need to be designed as a cloud-native applications. It means that they should follow 12-factor application principles, be horizontally scalable, highly available, and so on. And also they should have official Docker image and Helm chart. Third principle, decoupled architecture. Each component within platform should be responsible for a dedicated problem and perform independently. Combine it with open source based principles and we get a crucial advantage. Any component can be replaced without affecting the whole platform. Great. So how does overall architecture look like? Basic platform blocks go from data platform definition I shared on the slide earlier. Data platform designed to collect, then store, then process, then access, and manage data. Raw data comes in, and insights come out from the platform. Overall architecture looks clear and pretty simple, I think. In reality, of course, there are more aspects we need to care about. So each building block might contain sub-blocks dedicated to manage these aspects. For instance, management includes at least orchestration, observability, and compliance sub-blocks or responsibilities. Now we will start building reference architecture, discuss alternatives, and current trends. I would like to start with storage for the data. For the last few years, Lakehouse architecture has been rising. Lakehouse combines data lake and data warehouse architectures, and today it's industry standard. Lakehouse decouples storage and computation layers and allows to use one chip storage for structured and unstructured data. What is the most known, scalable, reliable, and cheap storage system that has a lot of integrations? I think it's S3. Today, S3 is not only service provided by AWS, but it's also open protocol that can be implemented by any third-party vendor. And among other implementations, I want to highlight Minio. Minio is a high-performance S3 compatible object storage which open source under AGPL license. And it's Kubernetes native solution. Apart from available Docker image and Helm chart, it has Minio operator and Helm chart for the operator. Latest operator version 6 allows declaratively define tenants and jobs similar to other Kubernetes resources. So we define tenant with its default state, like buckets, policies, users, put definitions into Kubernetes cluster, and operator deploys Minio cluster in minutes. There is an alternative solution, especially if AGPL license considered as a risk. Apache Ozone. Apache Ozone is a high-level project in Apache Software Foundation. It has a free API, and it can be deployed to Kubernetes. Also, Apache Ozone has an official Docker image, and there is a PR in progress opened by me to release first version of the chart, of the Helm chart. Great. Now we know where to store the data, but actually how. Lakehouse architecture comes with new data formats. I'm sure you heard about all three formats many times in the last few years. They support schema evolution, ACID transactions, role level changes, time travel queries, and of course they are open source. Today there are a bit less hype and hollywars about which format is better because at the current state they are very similar and moving even closer to each other. There is a new trend on eliminating implementation details and providing common interface on top. At least two initiatives to implement this, Delta Lake Uniform and Apache Xtable, both quite new and evolve very fast. I think whatever format is chosen today, it will be not so important tomorrow. I mean, today it's more of a question what you believe in and like more. For instance, personally, I like Delta Lake because I remember it had better performance results in benchmarks. But for reference architecture, I would choose Iceberg for now because at the moment it has more integrations than others. Great. We have the first platform block in place. Now let's move forward and have a look at how data should come into the platform. Data ingestion. It's really hot topic, and it's still an evolving area, especially in open source world. What are the requirements for data ingestion tool? First of all, it should have a lot of connectors by default. Then the solution should be extensible because apart from all connectors to support popular systems, you might want to get data from something specific for your business. It should be flexible in how data get in, how often, inability to tweak this behavior. And of course, the tool should be easy to operate. Here, I would include observability, user-friendly interface, API, and so on. And probably Airbyte was the most hyped product here for the last couple of years. It's open source tool, and the license only limits users in providing Airbyte as a managed service. Airbyte has a lot of default connectors, and also it allows to write local connectors. It has a Docker image and Helm chart, and Airbyte 1.0 has been released a few days ago, which means that the product finally achieved necessary stability on how it should look like. What about alternatives? Well, I would like to mention DLT, or Data Load Tool, because it seems to be next hype product for data ingestion. It has Apache 2.0 license, many connectors, and it's very extensible because it's actually a Python library. What it means in context of data platform development. It means that DLT can be used for implementing lightweight data ingestion processes. But it also means that we need something on top to manage DLT jobs. DLT has few suggested options on how to run and schedule it in production, and we will discuss our choice later. But for now, I would like to stop here. And by the way, DLT 1.0 also has been released a few days ago. I'll put both Aerobyte and DLT to architecture diagram because I believe they actually can complement each other rather than compete. Next, I would like to have a look at how to process the data. Probably it's not a big surprise to see Apache Spark here. It's a famous project that designed for high throughput data processing. It has multi-language API and it's Kubernetes friendly. Coming Spark 4.0 drops many very old dependencies, introduces variant data types, makes Spark Connect generally available, and many other features. I'm not sure anything can replace Spark in the nearest future in that niche, so let's put it on its place. However, despite Kubernetes support, it's still challenging to run and manage Spark jobs in Kubernetes. There are two cases on how users might want to process data with Apache Spark: submit Spark application or just execute SQL query. Both cases can be managed by third-party tools. Let's have a look at these tools. And the first is Apache Coody, another great project in Apache Software Foundation. It's a multi-tenant gateway to provide serverless SQL on Lakehouse platforms. It allows seamlessly execute query from a client, and then Coody will manage necessary engine, not only Spark, and access to this engine. Coody provides authentication and authorization, and it supports sharing engine resources. For instance, it can run new Spark driver and executors for each connection, for each user, for a group of users, which is useful in development environments, and one engine for local setup. Apache Coody has an official Docker image and Helm chart, which distributed with every new release, but the community and myself working on separate Coody and Helm chart releases. Okay, next, submitting Spark applications. Submitting Spark applications to Kubernetes cluster can be solved with Spark Operator. Today, good question is, which one? Spark Operator project, originally created by Google, was migrated to Kubeflow community that seems to have a good plan and vision on how to continue project development. And you know what? Spark Operator 2.0 has been also released just a few days ago. But there is another candidate coming, Apache Spark subproject called Apache Spark K8s Operator. It's under active development and not released yet, but it allows to define Spark applications in declarative ways similar to Kubeflow Spark Operator, and also declaratively define Spark clusters. Both projects have or will have soon Docker image and Helm chart, and they, of course, designed as Kubernetes native applications from the beginning. Okay, let's put mentioned projects on the architecture diagram. Both we put to management layer. And now what about accessing data? Can we use Spark for serving data as well? Of course, Spark would work great for heavy data, heavy data science and other batch processing on-demand use cases. So let's add Spark to serving layer as well. But what about other use cases like accessing data from BI tool or ad hoc queries? Spark will not work if latency matters because it is designed for high throughput workloads. Then what to choose to complement Spark in the serving layer for low latency queries? And I think it's Presto. Presto project is governed by Linux Foundation, and it's really fast SQL engine that designed for interactive and ad hoc queries. Presto has multiple connectors and allows to run federated queries, so it can be connected to different systems and combine data from these systems in one query. Presto has official Docker image and Helm chart, shameless plug, created and maintained by me. So it's easy to deploy Presto to Kubernetes. Also, I would like to mention that last 2-3 years, the community has been working on Presto 2.0. The main idea to replace Java engine with engine on Velox. It's C++. It's not generally available yet, but it already works for some connectors and cases, and it's much, much faster. What about an alternative solution? It's Trino. Trino was forked from Presto some time ago, and so it has the same use cases and main features by design. It changed quite a lot from the original code base, but I would still consider Trino as a drop-in replacement for Presto and vice versa. Great. Now we have serving layer. What's next? Next, I would like to have a look at how to structure and schedule data pipelines. And it's probably quite expected to see DBT here. DBT is a data transformation workflow that allows to structure data pipelines in a SQL-first approach. It also allows to develop data pipelines following software development principles, including the coding, testing, providing documentation, etc. DBT Core is open source under Apache 2.0 license, but it doesn't have orchestration, so we need to use something on top. What it can be? Well, there are a lot of really great orchestration alternatives, but I would like to highlight Apache Airflow, one of the most popular Apache Software Foundation projects. It's highly extensible by design, so you can run almost anything in Airflow, including DBT workflows and DLT jobs I mentioned before. It has official Docker image and Helm chart, and is actively developing. Airflow 3.0 should be released next year, and I would expect that it will be able to run DBT workflows natively. But for now, we can use open source project maintained by Astronomer, one of the biggest Airflow contributor. The project called Cosmos. It decouples, it decomposes DBT workflow into Airflow jobs, what allows to use Airflow orchestration capabilities like rerunning jobs, alerting, and so on. Great. Let's put them all together to the architecture diagram. And what's next? I'm almost out of time, so I want to focus on one necessary component in the data platform, data catalog. We need data catalog to find the data, which sometimes can be quite challenging even in small organizations. We need data catalog to observe how data looks like and how it changes over time. We need data catalog to govern our data and provide appropriate access to the data. Also, ideally, it should be a unified tool, which can be used by humans and other tools. And of course, it should be data source polyglot. You probably know that open source data catalog is a really hot topic this year. And today panel discussion was a great opportunity to know more about challenges and trends in it. We have at least 3 new players, Unity Catalog, Apache Gravitino, and Apache Polaris. They're under active development at the moment, but evolving very fast. But also, there are few catalogs that exist for some time, such as Data Hub and Open Metadata. Both look great and can be easily used in Kubernetes. So it's hard to make a decision which one to pick for our architecture, but let me choose Data Hub for our data platform architecture. Great. Do we have everything we need in our platform now? Of course not. There are few undercurrents that always exist in any platform, like monitoring, logging, security, FinOps for cost management. But I intentionally decided to leave them out of scope for this talk to keep focus on data platform problems. And final problem I want to discuss is how to actually run all these tools together on Kubernetes. We need a glue for our open data stack to make it open data platform, something that can integrate components with each other by providing URLs to necessary places, creating policies in one component to another, and so on. Something that can take data platform definition from Git repository and create the platform in Kubernetes cluster. Something that can continuously deliver component updates, something Kubernetes native. And it is Argo CD. Argo CD is open source GitOps tool for continuous delivery on Kubernetes. Remember that we have Helm chart for all components that we choose. With Argo CD, we just need to define how these Helm charts need to be installed by providing a shared configuration and deployment order. For instance, because Minio, for instance, should be deployed before other components. Then we put these configs to Git repository and simply configure Argo CD by providing a source, our Git repository, and destination, our Kubernetes cluster. Wait a few minutes and get open data platform up and running on Kubernetes. Cool. We just finished building the solution, so I would like to make a short summary. In this talk, I described a way to build an open data analytics platform with opinionated set of open source products, and also a way to connect all moving pieces together into cloud native solution with Kubernetes and GitOps approach. And I'm saying a way because, of course, there are alternatives in each step, and data tools landscape changes rapidly. One last thing I want to share, there is at least niche demand in data platform like this. I know there are a few in-house implementations, and I built one of them, but there is no open source ready-to-use implementation at the moment. Who knows? Maybe it is the next hot topic in our rapidly changing data domain. That's it, what I had to say for today. Feel free to reach out to me and connect in LinkedIn. I would be glad to discuss other opinions and learn new tools. Thank you, and goodbye.